So for today's presentation, we're going to be presenting a practical overview of post-quantum cryptography. We'll walk you through what PQC is and why it's needed. We'll also touch base on some concepts of quantum computing, go over the selected PQC algorithms, and then we'll end with some practical information for implementing PQC in SSH and HTTPS services. And we also hope that after this presentation, you guys will be motivated to start your own path to implementing your own PQC on your systems.
But before we begin, I'll give a quick introduction about myself. Hi, my name is Ramirez. I'm currently a second year at UC Berkeley studying applied mathematics and data science. A few things I'm a part of is WICS, which is the Women in Computing and Data Science Club, where I'm the project's committee member as well as the marketing chair. I'm also an MPS Scholar Mentor, where I mentor undergrad students who are majoring in STEM-related majors, as well being a part of the CalTeach program, where I am a teacher assistant at elementary schools teaching kids about math.
Hi, I'm Adam Ramirez. I'm a third-year applied math major with an emphasis in CSC, attending UC Merced. Some things I'm a part of on campus is the SADL program. I'm a SADL research intern, which stands for Students Assessing Teaching and Learning. Along with that, I'm also the president of the ACM chapter at UC Merced, which is the Association for Computing Machinery. And at UC Merced, I also presented some workshops on PKI, Linux, and cybersecurity. So to start off, what is post-quantum cryptography? I provided a little definition of here. It's cryptography focused on developing encryption algorithms that can run on classical computers, but withstand attacks from future quantum computers. I also provided some other ways PQC is referred as quantum safe, quantum resistant, and quantum proof encryption. So PQC algorithms are based on mathematical techniques that are believed to be too difficult for quantum computers to solve. So although quantum computers will be powerful enough to break current encryption algorithms, they don't fully exist yet. However, security experts say that it's important to plan ahead, in part because it takes years to integrate new algorithms across all computer systems. So why do we need PQC? I provided 3 points of why we need it. First is we need to future-proof our data and communication from quantum threats. PQC gives us the next generation encryption algorithms that will remain secure now and after quantum computers come online. Second, it will protect our data from quantum attacks. Quantum algorithms such as Shor's algorithm and Grover's algorithm, which we'll get more in depth along the presentation, are known to break or weaken our existing encryption algorithms that we rely on daily. Most notably RSA, if you guys know what that is. For instance, we want to make sure our online privacy, banking, and crypto wallets are secure from quantum computers. And lastly, for compliance purposes. NIST, or National Institute of Standards Technology, is already planning on deprecating current algorithms over the coming years. So it's a good practice in adopting security-related standards. In regards to quantum threats, Harvest Now and Decrypt Later is one of our biggest quantum threats. So Harvest Now and Decrypt Later is when bad actors and nation states are collecting encrypted data in hopes of decrypting the data once quantum computers come online. So by migrating to PQC algorithms now, we can prevent this attack in the future. And you're going to see a repeated pattern of us reminding you guys to implement PQC algorithms now instead of later. But before we dive into cryptography, I'd like to address one misconception, which is post-quantum cryptography is the same as quantum cryptography, which is wrong. They're not the same. So the difference is post-quantum cryptography, like I said at the beginning, is using classical encryption algorithms resistant to quantum computers. Where on the other hand, quantum cryptography is encryption algorithms using quantum computers. Now, Marie will give you guys a quick introduction on cryptography.
So before we get into talking about quantum cryptography, let's talk about classical cryptography. In general, cryptography is a practice of using math to protect information so that it's so that only intended recipients can access it. Whereas encryption is using specific cryptographic methods to convert data into a scrambled format. So the cryptography methods that we're interested in can be divided into 3 different types. First, we have symmetric encryption, which uses a shared key. Second, we have asymmetric encryption, which uses both a private and a public key. The public key is used to decrypt a message, and the private key is used to decrypt a message that was encrypted with the associated public key. And lastly, we have hashing functions, which are one-way functions that provide data integrity. So let's take a look at symmetric encryption. In this scenario, we have the famous Alice and Bob used in cryptography. As stated earlier in symmetric encryption, a shared key is used to encrypt and decrypt a message. So Alice and Bob meet somewhere and exchange a key so that they can communicate through secret messages. Alice has a message that she wants to send to Bob. She uses the shared key to encrypt her message. In today's world, she's most likely using AES 256 algorithm. The AES algorithm became a standard back in 2001 by NIST. It superseded DES, however, 3DES is still used in chip cards used because of legacy applications. Now back to our process. The encryption data creates a ciphertext of the message. At this point, if a bad actor, Eve, intercepts the message, she will not be able to access the original text. Bob will receive the encrypted message using the shared key, can decrypt it, and thus read the message. Although the process worked out nicely, the only problem with symmetric encryption is the process of sharing the key. There's really no secure way to share the key when Alice and Bob are located in different locations. So let's say if Bob is in Europe and Alice is in the US, it's not always practical to have either one travel to exchange the keys. But we'll see the solution to this problem with asymmetric encryption. So in asymmetric encryption, we'll use the same scenario with Alice and Bob, where we have Alice wanting to send a secret message to Bob. The main difference from symmetric encryption is that asymmetric encryption uses 2 keys, a public and a private key. The public key is used to encryption, whereas a private key is used for decryption. As another message she wants to send, Alice has another message she wants to send to Bob. In our asymmetric scenario, both Bob and Alice have created their own key pair, a private and a public key. They both publish their public keys on the internet. This allows anyone that wants to send encrypted messages to them use their public key to encrypt the message. As you can see, asymmetric key encryption eliminates the problem of using the shared key. In today's world, she most likely will use RSA 2048 algorithm, or more recently, elliptical curve cryptography, known as ECC. The RSA 2048 encryption process will generate a ciphertext. Bob receives the encrypted message, so he uses his private key to decrypt the message, and then is able to read the original message. So one thing to note, asymmetric encryption is slower than symmetric encryption for large chunks of data. This is why, in practice, asymmetric encryption is often used as a method to securely exchange symmetric keys. So once both parties have shared the key, they will use the shared key to decrypt and encrypt message thereafter. So the last encryption method I want to mention is hashing functions, which on the other hand are not encryption algorithms, but rather a one-way mathematical algorithm. It takes data of any length and converts it into a fixed length string called a hash value. It essentially creates a fingerprint of the data. It provides a way to verify the integrity of data or if the original data had been modified at rest or during transit. So as we see in the diagram, we start with the plain text message. Then we apply the SHA-512 hash function, which gives us a unique value, which is 64 characters long. We can then use a hash value to verify that the original contents were not modified. So for instance, if we added a single space to the plain text message, it will then generate a completely different hash value. So let's take a closer look at the SHA family hash functions. The different variations of SHA hash functions are distinguished in the number of bits they use for the hash value. So for instance, SHA-256 is a 256-bit hash. In computing, the bit is a single unit of data, and 8 bits equals a byte. A byte represents a character such as a letter, number, or symbol. So with a little math, we can calculate the length for the specific SHA hash. A SHA-256 hash is 32 characters long, a 384 hash is 48 characters long, and a 512 is 64 characters long. So using the OpenSSL command, we can generate the SHA hash values. In this example, we generate the SHA-256 hash value for the phrase hello world. I generated the SHA hash values for SHA-256, 384, and 512. I don't expect you to be able to read them, but you can see the differences in the length. As you could probably tell, the more the hash bits, the more secure the hash value. However, the higher the security, the more the computational and memory cost is required on the system.
So now we're going to give you a quick overview about quantum computing. So I think one of the best ways to describe quantum computers is to compare the classical bit with a quantum bit. So in classical computing, we all know it's either a 1 or a 0. But in quantum computing, it's a bit different. The bit is then replaced by a quantum bit, otherwise known as a qubit. So the qubit is geometrically represented by the Bloch sphere, and every point on this sphere, every point on this surface represents a possible quantum state of a single qubit. So mathematically speaking, the simple equation that we have right there near the Bloch sphere is the qubit quantum state. It's a linear combination of a 1 and a 0, or as a superposition of a 1 and a 0. So the coefficients alpha and beta are the probability amplitudes of the qubit collapsing either to a 1 or a 0 when it's measured. Anyhow, let's look at some of the properties of a quantum computer that are used as advantages over classical. So here we have a picture of a typical quantum computer, which looks like a golden chandelier. So when you see these types of images, you're often looking at a superconducting quantum computer, which runs at temperatures at absolute 0. So companies like IBM, Google, AWS, and Rigetti are already developing these types of computers. Other types of quantum computers that are based on trapped ions, neutral atoms, photonic-based qubits, and even Microsoft Majorna qubits. So let's focus on the 3 quantum properties that make a quantum computer so powerful. So the first one is superposition, as we talked about. It allows the quantum computer to process multiple possibilities at once, allowing them to process many inputs simultaneously. Next, we have entanglement, which allows qubits to be entangled, where the changing state of an on qubit immediately changes to the state of its entangled partner. So this results in faster and efficient processing of information over classical computers. Entanglement also helps in error correction by protecting the quantum information from decoherence. And lastly, we have interference. So quantum systems can be represented as waves. So using constructive and deconstructive interference, quantum computers can use this property to amplify correct solutions to the problem while simultaneously canceling out the incorrect ones. So as a result, interference boosts computational accuracy and faster calculations. There's also one thing to note. Quantum computers were never meant to replace our desktops. They were meant for solving complex problems that require large calculations. So just like our classical computers, quantum computers are useless without their algorithms. So 2 quantum algorithms that are basically driving the post-quantum race are Shor's algorithm and Grover's algorithm. So first is Shor's algorithm, which was developed by Peter Shor in 1994. This algorithm leverages superposition and entanglement. So this algorithm is great at finding prime factors of large integers. The most popular cryptographic algorithm that we use today, as I mentioned before, is RSA, which is based on prime factorization, which is broken by Shor's algorithm. So on this graph that I provided, it shows us the significant speed up in the number of operations required for integer factorization between the best classical algorithm and then Shor's algorithm. So on the top red line, it shows how fast classical computers will break any prime factorization. And then at the bottom blue line shows how fast Shor's algorithm breaks it. And as you guys can tell, there's a big difference. So in simple terms, Shor's algorithm reduces the time to break RSA keys from billions of years to weeks or even less. And then next, we have Grover's algorithm, which was developed 2 years later than Shor's algorithm, but it was developed by Love, Kumar, Grover. So just like Shor's algorithm, it leverages superposition, but in this case, it also leverages phase interference. Grover's algorithm provides a quadratic speedup over the classical algorithm. So we can look at this chart over here, and we see that we have n reduced to the square root of n. In the case of Grover's algorithm, the time to break a key from many billions of years to fewer billions of years using a brute force attack. So in the case, it just weakens AES instead of breaking it. Here I have provided some post-quantum encryption standards which were selected by NIST. NIST effort to develop these quantum-resistant algorithms began in 2016. Experts from dozens of countries submitted 69 eligible algorithms. NIST then released these 69 candidate algorithms for experts to analyze and to crack if they could through multiple rounds. I'm not going to go into all the technical details of each one, but you'll notice that the lattice-based algorithms are very popular among this. So first we have the ML-Chem, which was formerly known as Crystal's Kyber, and it's used for asymmetric encryption. Then we have ML-DSA, which was formerly known as Crystal's Dilithium, which was used for digital signatures. Then we have SLH-SSA, which was formerly known as Sphinx, and that's used for digital signatures as well. And then we have FN-DSA, which was formerly known as Falcon, and that is also used for digital signatures. I'm not going to pretend like I understand all the math behind these algorithms, so here they are. So there seems to be a lot of hype over quantum computers in the news. We know we have some that are real, and then we have some that are misleading. However, there are many companies making large investments in progress with their roadmap for reaching fault-tolerant quantum computers. So it's very important to improve the security of our systems with PQC algorithms. So just to summarize, our existing classical encryption methods are at risk going forward. So although there are mitigations for some of the algorithms, for instance, using larger key sizes, there also is a downside, because using larger key sizes can impact performance due to the increased computational workload.
So now that we covered PQC and quantum computing in general, we can take a look at a couple services and see how we can implement PQC to help secure them. So we'll first look at the SSH protocol and then HTTPS, but really TLS protocol. So SSH, or Secure Shell, provides a secure remote logins and remote command executions. We see that all three types of cryptography are used in an SSH session: symmetric, asymmetric, and hashing functions. So one thing to note, our characters Alice and Bob that we used in our previous slides are now replaced with the client and server. Instead of Alice and Bob exchanging messages, or SSH client, known as Alice, is exchanging messages with the SSH server, formerly Bob. So we start off with the SSH client starting a connection with an SSH server. These sessions are established through a sequence of exchanges between the SSH client and server. So once the TCP connection is established through SYNAC handshakes, the client and server will exchange the version information so that they can see that they support the same version. Then the algorithm negotiation phase starts, which determines which algorithms they both support and should use. If they don't have an algorithm they both support, the exchange will end up failing. Then we go into key exchange phase, where it will generate a shared session key for the subsequent symmetric encryption. Once the service request is issued, the SSH will then be established. So this entire diagram is generalized, but all three cryptographic types are used and thus have the opportunity to be hardened with PQC algorithms. In particular, the algorithm negotiation and key exchange phases. So now let's look at TLS with HTTPS. It follows a similar sequence steps between the client and the server as the SSH protocol, including the use of all three types of cryptographic algorithms. The Transport Layer Security, TLS, protocol encrypts data to protect it from unauthorized access from HTTPS. HTTPS uses TLS to encrypt communication between browser and the web server. We start off with the client or the browser initiating a connection with the web server. Once the TCP connection is established through Synapse, the client sends a client hello message to the server where the client server exchanges information such as version information, cipher suites, and a random number. The server responds with a server hello message that includes the selected cipher suite and server certificate that the browser will then verify. Then the client key exchange and key generation phases generate a shared key based on the random number provided in the client hello message. Then the changed cipher spec message determines the new symmetric key and starts the TLS session. And finally, the TLS handshake ends and the HTTPS session begins where the application data is encrypted. So just like the SSH protocol, the TLS protocol needs to be updated with PQC. TLS is used by other services such as LDAP and email, especially when Start TLS is used. So how do we implement PQC on SSH and HTTPS? Luckily, there's an open source project that helps with that. All the complicated cryptographic parts are provided through the liboqs, or the Open Quantum Safe System Library. The liboqs is a library of post-quantum algorithms and an API to access them. Existing infrastructure tools that we rely on, such as OpenSSL, OpenSSH, can be compiled with liboqs to provide PQC algorithms. So now we're going to walk through enabling PQC on OpenSSL. So our building environment consists of a virtual machine running Red Hat 9.5 with a minimal install, Git, GC DevTools, OpenSSL 3.2.2, plus the Devel packages. The steps for enabling PQC on OpenSSL are building and installing the liboqs library, building the OQS provider. Then you would want to configure OpenSSL with OQS provider, and then verify the configuration. The OQS provider is a plugin for OpenSSL 3 that adds supports for post-quantum cryptography algorithms. Starting in OpenSSL 3, providers were introduced as a plugin system for dynamically loaded cryptographic algorithms. The Open Quantum Safe project created OQS provider, which relies on liboqs library. So let's walk through the liboqs build and installation steps. We first start with creating the build directories for liboqs. Then we download the liboqs source files from liboqs Git repo. Then we will set the environment so that we create shared libraries and install it to the system directories. And finally, we call make and make install to build and install the libraries. So now that we have liboqs installed, we will build the OQS provider library following a similar procedure that we followed for liboqs. We first start with creating the build directories for liboqs. Then we download the source files from the Git repo. Then we set the environment with the paths from liboqs. And then finally, we can call make and make install to build and install the libraries. So after we install the OQS provide shared library and include the file, we need to configure the OQS provider in the OpenSSL configuration file, which is located in the /etc/ssl/openssl.cnf. We define the OQS provider and activate it as secure. So now that OpenSSL knows about OQS, let's verify it using the OpenSSL list. Providers command, which gives us the OQS provider info. OpenSSL also provides options to list various algorithms. Here we run the OpenSSL command to list key encapsulation mechanism, or KEM. We can see that the MLKEM is supported now. And one last check, let's list the key exchange algorithms. We can see the MLDSA and Falcon. So now we will be walking through building the PQC in the Apache web server using mod SSL. Since we already have OpenSSL enabled with PQC, the Apache can leverage that with mod SSL. Mod SSL is an Apache module that provides cryptography for secure web connections using SSL/TLS protocols, relying on the OpenSSL toolkit. So similar steps as the OpenSSH, we will install the Apache web server, enable the MLKEM, and then you'll want to test your HTTPS on the Apache. So now let's enable the key encapsulation mechanism algorithm in the Apache web server using the SSL OpenSSL configure command. Here we are using the MLKEM since it's supported in the latent versions of major browsers. After we start the web server, it should accept and support the new PQC algorithms. So now let's test the PQC connection using Chrome. As we can see, the connection is using the PQC algorithm. To tell you through, enabling PQC algorithms can be a bit underwhelming. Everything feels the same. You visit a PQC web server or PQC enabled service, but you know that the service is secure. Here Here, here we have a screenshot verifying an SSH session with PQC enabled. Even when OpenSSH enabled with PQC algorithms, it feels the same. But we know that quantum resistant, which is what we want.
So we only covered 2 services, but there's many more that will be vulnerable to quantum attacks. Firstly, I have PKI, which is the public key infrastructure, just like Marie mentioned with the asymmetric and symmetric encryption. Then we have blockchain and cryptocurrencies, and then we have email using the PGP and the GPG encryption. Also, popular messaging apps like WhatsApp, Signal, and Telegram use ECDH. And although these are currently sufficient right now, they will be compromised when quantum computers arrive. So thanks to a project known as the Open Quantum Safe Project, and specifically the liboqs library, we're able to start testing and migrating our services to quantum safe algorithms to prepare for quantum threats. So I compiled a list of companies that are already supporting PQC algorithms. So some notable ones we see is Mozilla, Google Chrome, Amazon, and Cisco. So what are the next steps after learning what PQC is and knowing the quantum threats that are coming soon? So knowing that the quantum threats are coming, there's no need to panic. There is still time to implement these PQC algorithms. So once then we start testing with the PQC implementations and configurations, practice your own crypto agility, and then start testing your own PQC today. And I'd like to leave you all with one last quote, and it's to encrypt like it's 2030. So I want to thank you guys for your time. We have our emails right there if you would like to reach out to us. And yeah, thank you.
Do we have any questions?
I saw his hand. Yeah, I think it does.
Thanks for the talk. I
course.
noticed that when you were listing the post-quantum algorithms that you listed asymmetric algorithms. Are there any symmetric post-quantum algorithms being developed? And if not, is there like a difference, with between classical and post-quantum asymmetric versus symmetric encryption?
Well, with the symmetric encryption, I don't know if there's I don't know any top of my head of the PQC, but the second part of your question was the classical, what was it again?
So I'm just wondering if because in classical encryption, there's symmetric would be used like if there's something like you need faster speeds or whatever. Is there a similar thing with post-quantum encryption, or is asymmetric quote unquote fast enough?
Yeah, I think, off the top of my head, I don't know, and I'm sorry.
Yeah, so first, with classical encryption, if you've been following it for a long time, you'll notice that the key sizes keep growing up because it's only computationally secure, and that as the classical computers get faster, smaller keys can be broken just by them.
Yeah.
So is there something similar with quantum encryption? I guess we don't necessarily know what the trajectory of quantum computers will be, but we have to keep increasing key sizes, because what that gives you also is this capture now, decrypt later problem.
Yeah.
Even if it is quantum safe, if the quantum computers get even faster, right?
So, wait, what was your question again?
Well, so is there something similar where you have where today's quantum safe algorithm? Well, first of all, we don't know if some new quantum algorithm will come out, but also if the quantum computers, once they exist, start
Oh.
getting faster the same way that classical ones have.
I mean,
And then will you still need larger keys for those quantum algorithms?
I would assume so.
Yeah.
You know, as time goes on, obviously there's
Yeah.
going to be more advancements within the
Right.
quantum computing. So I just would say, you know, keep up to date
Yeah.
as long, like right now for classical encryption, keeping up to date with this quantum computers is something like you have to stay in the know.
Yeah, well, one other thing is, three of the four algorithms were for basically for hashing, right? So when you do the SSH exchange, depending on your settings, you may also be using the crypto to verify that you're connecting to the right host, avoiding man in the middle. Same with TLS.
Yes.
So would you have a quantum safe algorithm for that would be included in for example, the OpenSSL setup that you showed?
Yeah, you know, the library we provided, the liboqs, is a library with PQC algorithms. So,
For both?
So if you want to look more into that, I
Yeah.
would suggest you to,
Okay.
yeah.
Right, because and then like there'll be a way to sign the keys, just like with regular current keys to validate websites and SSH servers and stuff. Yeah, okay.
There's nothing, you never get something for nothing in life. How much slower is using liboqs than using, say, elliptical key cryptography nowadays?
Wait, can you repeat that?
I'm presuming that using liboqs is slower because you're doing a more sophisticated, computationally intensive calculation. Have you measured how much longer it takes to, say, transfer a large amount of data with HTTPS with liboqs?
So with liboqs, it's a library with many algorithms. So to compare that with, wait, what were you comparing it? You said liboqs with.
I'm presuming, which could be false, that liboqs is performing a longer, more sophisticated computation, which is still basically calculationally intractable without a quantum algorithm. But are those algorithms just different, or are they longer as well, so that they, would encrypting your disk, another thing you could try and discuss in a talk like this, would that just be intractably slow if you used liboqs to encrypt and decrypt the storage medium? Is liboqs actually being used to encrypt, could I, on my laptop,
Yeah.
yes, it's possible, but would it be feasible?
Well, I was just going to add on to that. A lot of the initial work with post-quantum encryption is focused on the asymmetric stuff right now, because that is has been identified as the most vulnerable to a potential quantum attack. As was mentioned earlier in the slides, I think that even though like AES is theoretically is vulnerable, the attack profile basically as the key size grows still could possess a pretty big, like you could just keep growing the keys and that would be some mitigation. So they are developing symmetric quantum safe algorithms. However, I think a lot of the focus right now is on the asymmetric for like the key exchange, because that seems to be the most vulnerable.
Yeah.
Oh yeah, of course. You could do all your encryption like that, but it's still going to have the same problem that classical, asymmetric has, where it's just not super fast. But I think back to I am interested about as well. What are the performance implications of the currently available post-quantum algorithms, if you know about that?
Yeah. I have. Yeah, I don't really know. But after you could come see me, and I'll try to figure out an answer. Yeah. I would say I was really into cybersecurity, and then I remember in 2020 during the pandemic, I actually took a quantum computing course, and then from there I just learned more about it and became more interested in it.
Have you seen a show called Devs?
Yeah.
What's your opinion on Devs?
I thought it was pretty cool, like just seeing it, but then like some parts were just like kind of crazy, like just like the plot, like the storyline with it. But like that like also like made me more interested in quantum computing because we both took the class together. So
So then, because you already answered why you got into the quantum cryptography, how about you?
oh, I was also interested when we took the class during the pandemic as well, because I'm pretty sure it was with the coding school. So, and it was taught by like MIT graduates, so nice.
I mean, just as a demo, if it were me, I would just pick a giant file. I would encrypt it with RSA and measure the time, and I would encrypt it this other way and measure the time, and then do the same way with disk decryption. So it should be.
regards to that. The performance implication question is a little bit like it can kind of be meaningless at some point because a lot of we have like so many different encryption algorithms available today, but part of the reason why we almost always are using some variant of AES is because we have hardware optimizations for the AES encryption. So really, you're not going to get anything that is like as fast as that, as fast as the stuff we've optimized hardware-wise. But if we're moving to a more post-quantum, quantum-safe world, inevitably we'll be developing hardware acceleration for that kind of stuff to bring it up to speed with what we would expect for a modern encryption hardware.
Yeah, and even with hardware-accelerated AES, you can see the performance difference if you encrypt and decrypt a full disk. I mean, if you boot from an encrypted disk, you can see at the startup it takes longer. So, Well, that was a super great talk. Oh wait, one more question.
So I'm jumping in. I missed the whole talk and I lament it. I haven't seen this topic in about 20 years. I was researching it in grad school at the time. But what have you, and it was already commercialized to an extent. I remember Magic Q. And there's already experiments like I don't know, remember, like in Switzerland under Lake Geneva, they had like fiber optics that had done like some quantum encryption already. And like Magic Q in Canada and others had already like commercialized like for banks for transactions, quantum encryption keys and stuff. But what have you seen from like maybe like online regarding like quantum encryption schemes from like adversary state actors? There's a lot of that online, but I just don't know what's the state of that. Have you seen any of that?
No,
Like
I
what's,
haven't.
no? Like if what on what's the, maybe something to look into. I don't know.
No, yeah.
Because I know they claim a lot, but it's hard to prove these things, right? It's like it's hard to take these things at face value, right? Just look at it in a paper, but so anyway.
Thank you.
What's coming next, right?
No, yeah.
Yeah. I mean, I know they're working on hardware optimizations for some of these lattice-based algorithms, but hopefully by 2030 we'll have it, if not sooner. Because, I mean, I think people have been using at least some lattice-based algorithms. I think they're used like in some real-time devices like cell phones already. So I don't know if what hardware is used to help accelerate that, but if it's not, it's coming for sure.
Well, thanks to you guys for a great talk.
Thank you, everybody. Thank you. I really appreciate it.